Good afternoon. This is Dr. John Galbraith. Welcome to the soil webinar series, the introductory level, May 28th, 2015. Today we'd like to talk about soil structure and its importance. Let's begin by introducing myself. I'm Dr. John Galbraith. I'm a soil information extension specialist in Blacksburg. My background is primarily soil genesis, soil survey, soil classification, wetland soils, but I use my soil knowledge in numerous different application fields. Today's webinar explains soil structure and its importance. We'll talk about different types and shapes of structure, how structure forms. We'll describe how to describe soil structure, the relation between structure and texture, and the relevance of soil structure to soil health will be included as well. This is a list of today's topics. And this is a list of the learning objectives for today's webinar. Well, let's begin with just a little bit of background information. The importance of soil structure. And this picture of a thick soil crust is impeding seedling emergence of soybeans. And this illustrates the importance of having good structure, avoiding the formation of soil crust, and having good water-stable aggregates. You can see some of the water-stable aggregates on the surface of this crusted soil. These small, what looks like particles or rocks, are actually just small, stable aggregates. The smooth silver areas of the crusted zone is where the aggregates have broken down completely into sand, silt, and clay. Well, soil structure influences the rate and the amount of roots, air, and water movement through soil, and we have to have that exchange from the atmosphere of gas, and we have to allow water to penetrate the soil instead of running off in order to have good plant growth. But we also need to have the ability of roots to grow through the soil. And where do they grow? Well, they try not to grow into aggregates, but they grow primarily between aggregates. Well, poor aggregate stability causes this crusting, and again, if we have crusts, then we're going to have decreased infiltration, which results in increased erosion and runoff. And simply put, better soil structure means better soil health. Well, let's talk about the shapes and the most common occurrences of different shapes of soil. At the soil surface, in other words, right at the top, we should expect either granular structure as shown in the picture on the slide, or subangular blocky, and that is partly use dependent and it's partly texture dependent. And just beneath the surface, then, we really should expect either subangular blocky or platy structure. The platy structure may be naturally formed, or it could be from compaction. So depending on the reason that we have platy structure could tell us whether we have a problem with the soil or whether we just have a natural soil that has this natural shape of structure. I'll tell you how to tell those two apart. In the subsoil, we have either prismatic, columnar, subangular blocky, angular blocky, wedge shape, or thick platy. Again, depending on the situation. So more variety in the subsoil than we have at the surface. Well, let's take a look at some of these structures. And if you look at these granules, you can see that they are primarily rounded. They don't really have many flat surfaces at all. This would be really good condition. This is what we would like to see in most loamy textured soils. It's not going to be possible in all the sandy textures, but it should be possible in the loamy textures. Well, here we have subangular blocky and angular blocky. And the subangular blocks, as you can see on the left-hand picture, have rounded corners. Some of the corners are rounded. They have multiple shapes and multiple sizes, and also, I guess, multiple surfaces. So rather than having a rounded, this one is primarily rounded, but it's very, very large compared to the granules. But more of these have at least one surface or one part of one surface that is flattened. And that's why we call it subangular and why we call it blocky. So it's really a combination of size difference and then just shape difference. Now, a few of these angles are the angle of the intersection of the surfaces, a few of these are fairly sharp, but most of them are sub-rounded. And in this particular slide on the right, you can see that the edges of this aggregate, first of all, it's quite large. This came from deep in the subsoil and from a limestone soil with quite a bit of clay. But you can see for the most part, there's a lot of right angle edges on here, surfaces that intersect at 90 degrees. And so that defines the sharp edges, and the intersection at 90 degrees defines the angular blocky. And typically these are soils that have more clay content in them. Well, we have two types of structure that's very similar. One is called prismatic, shown on the left. The other is called columnar, shown on the right. And essentially both of these form by the dominance of vertical cracks in the subsoil. So you're not going to see this at the surface, but in the subsoil you may see it. And again, if we have vertical cracks, that's going to be very, very easy for water, air, and roots to pass from one part of the soil to another. So this is probably a pretty good indication of good quality soil. However, the columnar structure is an indicator of poor quality soil. And this is because in order to form these rounded tops to the prisms, then we need to have sodium in the soil. That sodium causes physical and chemical problems that make this soil not as good on the right as the one on the left. So we don't see much columnar structure in Virginia, but if you do see that, then it's an indication of poor soil health. There is a type of prismatic structure that's associated with frangipans that is not shown in this particular slide set, but those soils again are an indicator of poor health. But when you can easily extract a column of soil, or I'm sorry, a prism of soil out of a soil pit, and it breaks apart easily into smaller units, then you have good quality. Well, this particular shiny feature in the soil is where shrink swell clay moves. And in other words, when it wets up, part of it moves faster than other parts of the soil, and it causes this slick, shiny surface to form. Well, this surface may form at contradictory angles, and when those angles intersect, then you end up with wedge-shaped aggregates. And here's a good example right next to the tape of one that looks like a triangle. And so wedge-shaped aggregates indicating shrink swell clay and some concerns about the subsoil. Now here's the thin platy structure that might naturally form from freezing. In the winter time, you get moisture in the upper part of the subsoil, and this would occur just below the topsoil, and you would get ice lenses that form parallel to the soil surface, and when they do, they cause compaction both up and down, and that's what creates this platy structure. Quite natural, but the secret is that these are very thin. They often form in the E horizon. All right, let's talk about compound structure. Again, we showed a picture of the prismatic structure a couple of slides earlier, and you saw, let's pretend that one of these is a prism that you can pull out of the soil. But then after you pull that out of the soil, if you put gentle pressure on it, it breaks apart into blocky aggregates. They use the word PED here. Aggregate is a little easier for most people to understand, so I use the term aggregate. But this is quite common to have aggregates that part from a larger size into a smaller size. Well, now let's talk about other masses in the soil that are actually not soil structure. And without soil structure, we have clods with incoherent textures. So, in other words, if the texture has enough clay and silt and organic matter in it to be coherent, then if we don't have structure, we will form massive clods. If we have a soil that does not have clay or organic matter, then it will typically that would be a very sandy texture, either a sand or a loamy sand texture. And in that case, then we'll have non-coherent soil, and it does not form clods. In fact, it falls apart as single sand grains. So if you could insert the word single sand grain, then you would be able to relate that to the texture where we get this kind of structureless condition in the soil. For all other textures that have more clay or more organic matter, then we get coherent masses that we call clods. Okay, we also have some unusual shapes, desiccated and divergent shapes. We also have crusts, both bare soil and biotic, and we have rock structure, which is really just thin layering. It's either the precursor to rock formation or it is a remnant of rock formation. So we can get the precursor in flooded deposits. That would include deltas, floodplains, uh, lake bottom sediments, anything like that, marine sediments. Or we can get leftover remnant layering from bedrock weathering. Well, here we have a picture of that single grained, non-coherent. So I termed it coherence, but this is actually a non-coherent material. This is what it looks like when it's dry. This is sand and structureless single grain when it's wet. It will hold together, but it's really just water holding these sand grains together. As soon as this mass of soil dries out, it will fall apart and separate into individual single grains of sand. Again, the textures here are either sands or loamy sands. This massive coherence that we see on the right is in a mine soil, and you can see the marks left behind by the digging tools. That's not usual in a soil that has good structure. If I inserted a digging tool into a soil with good structure, it would separate between the aggregates. But since there are no aggregates here, this is dense, compacted, root limiting. Then we can see the marks left behind by the shovel and the knife. Well, here are these unusual desiccated masses, and again, not really soil structure, but it's something that maybe is a precursor to soil structure formation. This is really the bottom of a lake or a pond that has dried out, and you can see the polygons that formed as this began to crack apart. And here you can see this is dredged material, kind of silty, that started to fall apart. And this is the beginning of the formation of soil structure. And so these big polygons formed as this soil dried and cracked apart. So this was very, very wet and silty. And these polygons are about the length of the shovel, so about 12 inches long or tall. On the right, we see divergent structure, and this is a compacted layer right below the plow line. And you can see, though, that the shapes of these are quite irregular. This is not a usual shape. This is not a predictable shape. It's not a consistent shape. They're either large, they can be small, but they just have no particular pattern. And down below in the lower right is a close-up showing these different shapes. And here we have some sharp edges, but look at the number of faces or surfaces that we have on these. And these are not aggregates. These are masses. They're they're material that has a shape, but it's an irregular shape. So this doesn't fit with any of the others, but it is a surefire sign of compaction. All right, we have crusts, and this at the top we see a crust in a silty soil. Again, this little dark area is where the water-stable aggregates accumulated. The lighter zones, that's where the loose silt, sand, and clay particles have settled out. Some of the crusts, and this is really just platy structure that forms at the surface. So this has not been underwater, even though it does kind of crack into a polygonal shape. But this crust is probably only just a centimeter or two thick, as opposed to the 12-inch thick polygons that formed in the lake bottom or dredge sediment. And here we see some cracking and polygon formation of a crust surface. But this one you can see has a gray coloration in parts and is kind of darker in other parts. You don't really see washed out particles or aggregates. You can see lichens. Here's mosses. This is algae and bacteria and some fungi. And essentially this is a biotic crust. In other words, these are microorganisms that are living on the surface, and their growth helps to hold soil particles together. So this is not a good sign of soil health. This is where either ponding occurs, temporary ponding, or where you might have nutrients at the soil surface or on the soil surface but not in the soil. So there's very few higher plants. There's one small grass plant here, one probably sedge right here, and some willow. But that's about it. And so the biotic crust is helpful in the western United States, but it's not that good of a sign here in the eastern U.S. Well, here we see thin layering from flooding, and this is the precursor to bedrock formation. So as this material would be deeply buried, these thin layers would translate into layering in the bedrock that would form from this material. Now that's going forward. This picture shows coming backwards. This has already formed into a rock, a metamorphic rock in this case, and is now weathering. And as it weathers, you can still see the thin layering left in from the original bedrock. But neither one of these are considered soil structure. These are considered rock structure or rock layering. Well, here's a quick quiz for you then, just a reflection. Are all soil crusts signs of bad soil health? Well, my answer to that would be no. That in the western United States especially, that a biotic crust is actually a sign of good soil health, and that erosion increases when a biotic crust is removed in the western United States. In the eastern United States, the soils, the crusts that we're most concerned about are the ones that form over silty soils and form in bare soil. So the biotic crusts are not a direct sign of bad soil health, but they do make us wonder why we have the absence of higher plants and a predominance of microbes growing on the surface. So cause for concern, but not really a sign that the soil is in bad condition. Okay, structure forming processes. Let's talk about the shapes and how they come together. So essentially we have in this graphic, we have the white circles, and these are meant to be sand grains. Well, how do sand grains hold on to each other? They're not charged. They have no attraction for each other. So how do they hold together into masses? Well, they don't often if it's just sand. But if we have some silt, some clay, and some humus, then we can hold the sand grains together, and the clay and the silt and the humus settle in between these particles and act to hold them together. The clay and the humus are charged, and so they have electrical attraction for each other. They also have physical attraction for each other. So the humus binds and the clay bind the sand particles together from within, and it also get coatings on the outsides of the aggregates that are either organic matter, iron oxides, or humus. That further stabilizes the aggregate. All right, well, what other processes help to form soil structure? Well, we saw drying. Desiccation was the precursor to soil structure. Well, here are some prismatic shapes, and then these break down into smaller angular blocking shapes. So how did this form? Well, it could be from desiccation. Wetting and drying allows for a little bit of shrinking and swelling between these prisms, and so that creates a stable repeated surface where water moves on a regular basis. That's also where the roots want to grow, because that's where the water is. That's also where the nutrients that get weathered and released in the upper part of the soil, that's where they are going to enter these cracks and move down into the subsoil. So the roots want to follow where the nutrients and the water are, and then the rest of this mass of soil absorbs water and nutrients from these cracks, and then encases it into the middle of these larger aggregates. Well, shrinking and swelling is another way that we form aggregates, and I showed a picture earlier of the wedge-shaped aggregates. This soil on the right has quite a bit of clay. It also has a lot of organic matter, and so we're going to have good strong structure formation here. But also freezing and thawing. I showed a picture of the platy structure in a previous slide, and that was formed from freezing and thawing processes. And if you go out into your yard or any kind of soil area in the late spring, you'll see areas that have the effect of freezing and thawing. They fluff up the soil when the ice crystals form, and then the soil collapses back into its original location after the soil thaws out. Well, here we have the idea, we're talking about humus and how it binds soil particles together, and clays do the same. So this soil that is a picture of a soil with a vigorous root system, pretty good aggregation, and nice dark colors. That looks like a healthy soil. On the right, we have a graphic showing us all the different organisms that might affect soil formation, and we'll go into that just a little bit more detail later. But essentially they affect formation both physically, and then they also affect it by the release of materials that help bind the soil together and feed the microbes. So actually microbe life and death does play an important part in structure formation, as does earthworm activity. Well, when we describe structure, we can give it a grade just like we would grade a test in a course. So starting at the top, grade 3 would be the best grade you could get, and grade 0 would be the worst grade. So of the soils that have soil structure, it's either going to be strong, moderate, or weak. And the difference between those three is explained here. If the soil has no natural soil structure, it may have shapes, it may have masses, it may have layering, but if it has no soil structure, then it is called structureless, and then it's going to be described by its coherence. It's either non-coherent, single grain, or coherent, massive. This is a close-up of a soil where we have moderate structure in the upper part until you hit the gravel line, and then we have very weak structure in the layer that has the gravel. And it'd be hard to imagine how aggregates could form, but also this would be low clay and high sand because of the higher energy. This is a stream terrace deposit. And then down below that we have bedrock. and so we have rock layering. So here's just an example of three different types of structure. All right, when we describe the structure size, it's a little bit complex. And so we have a we have a table here that we can use. So if the soil is thin and platy, we use this to separate the different sizes. And these sizes have terms. And so those terms are shown in the manuals that accompany description information for soils, and I'll discuss that in the very next slide. So we have a column for platy and the sizes. We have a column for prismatic and columnar, one for blocky, and one for granular. And this is the reference I was talking about. It's called the Field Book for Describing and Sampling Soils. It's a free resource. It's available through this USDA website, and I would recommend ordering one if you think you have any interest in having one. They're quite handy, they're free, they're waterproof, they last for years and years and years. This contains all the information for describing a soil, but what it contains here is some nice graphs that show not just the size. We had the size on the table before us, but this gives you the name, the size range, and the shape. So you get all of those. So let's pretend that I have a piece of prismatic structure and I want to compare it here. Well, I would grab that prism and I would hold it up, and if it fell between these two lines, in other words, if it was intermediate in size between the upper drawing and the lower drawing, then it would fit into the fine prismatic size. Now there's not pictures for all of these because it would not fit on the page, but it does give you the size range. There is a picture for all of the angular blocky and subangular blocky, all of the plates and all of the granules. So get yourself one of these books. I think you'll really enjoy it. Well, we did go over the shapes a little bit earlier, and we also talked about masses, layers, crusts, other ways that soil holds together. But these are the ones that we described: subangular, blocky, angular blocky, granular, prismatic, columnar, wedge, and platy structure. Let's put it all together, and we have here a picture of what would be moderate, medium size, moderate grade, meaning holds together fairly well, but there are some pieces that fall apart under gentle pressure. We have medium size according to the charts, and then the overall shape is subangular blocky. There are some flat surfaces, but many more of them are rounded, have rounded edges and multiple sides. Well, next we have a picture of the texture triangle, and this is just a reminder of the different textures. Again, when we talked about sandy textures, we're only always talking about these two in the lower left hand corner, sands and loamy sands. Sandy loams have a lot of sand in them, but they're not really a sandy texture because the last name is loam. It's a loamy texture. These are the loamy textures here. Okay, just a reminder of what the different textures are that we might be talking about. So let's talk about the relationship between structure and texture. Well, sandy soils, loamy sands and sands, have little structure, if any, and clay textures have abundant structure if they're not compacted. The sandy textures have lower water holding capacity, lower organic matter, and fewer microbes. They actually support fewer microbes because of the lower organic and lower water holding. And so they also have fewer earthworms. Earthworms don't like to ingest sand. They have fewer insects and fewer roots. So add all of that together, and sandy textures have weaker structures. Okay. In sandy loam soil textures, we get weak to moderate subangular structure, and that's the most common structure that we have. So very little structure in sands and loamy sands, but subangular is the most common in sandy loams. Now at the soil surface, in textures that are finer than sandy loam, if we're uncompacted, then we have granular structure. If we get compacted textures, then we're either going to get subangular blocky structure or platy structure. And this would not just compacted surfaces, but plowed surfaces as well. This is what it's going to break apart into. If you let that soil form over time, then it will eventually reform granular structure. But if you continuously disturb it or compact it, then you're going to get subangular blocky or platy. And clayey surfaces tend to form granular structure that they shrink and swell and crack apart more easily. Again, the review of what actually happens as soil structure forms, we get oxides, iron oxides, and in the Piedmont, the iron oxides are very, very abundant, and so they coat the aggregates, and we get very stable aggregates, at least in the subsoil where the oxides are. In the topsoil, we may not get very good aggregates. Just depends on whether the soil has been eroded or not. If we have that sandy loam, white sandy loam surface that we often get in the Piedmont, we probably won't have very good structure there. So what are we looking for as signs that we would have good structure? Well, we'd have to have abundant oxides, abundant organic matter, and abundant clay. Sandy soils are low in all three of these, so they have less structure and weaker structure. Starting to form a pattern here between sand, high sand content, and poor structure, or absence of structure actually. Then we get wetting and drying, freezing and thawing, and shrinking and swelling. But essentially, soils that hold more water or have expansive clays tend to have better structure. And soils that are always wet tend to have poor structure because they don't go through the drying part of the process. Well, here we see some organic textures, and this organic matter is laid down in layers as plants die. And so that's why we get thin platy type structure in these sediments. You may not find much structure at all, but if you look closely, I think you can see some horizontal lines, and that's where the platy nature would come in. What about soil health? Compaction from humans is a major cause of poor soil health, and that can cause thick platy structure, which prevents root growth, and it prevents air and water movement. Remember, we in the prismatic structure we saw lots of vertical cracks. Well, here we see one vertical crack below the surface. Most of the cracks are horizontal. And look at the roots. They're trying to grow horizontally. There's a few that are trying to grow vertically right in the very surface, but this has had to been plowed again, and recently. But in this compacted zone right here, we would call this a plow layer. In this compacted zone, you can see I lifted up the whole surface of this soil by putting my shovel in, and then these horizontal cracks appeared. It's very, very, very poor quality in this case. And then again, crusting that forms after a loss of structure. That's typically due to having a high silt content in the soil and having no residue on the surface. So when we do get heavy rains, the raindrop impact is able to soften and dissolve these aggregates, and then they separate into individual silt, clay, and sand particles, and that's why we get a crust forming. When they dry out, they form the crust. So two things have to happen. You have to expose the silty soil to raindrop impact, and then you have to so you do that by removing all the residue after farming and not leaving enough residue. And then secondly, we have to have the raindrop impact, and then it has to dry out. And if that happens, a crust will form. Okay, well, looking at root growth as an indicator of soil health, look at how all of these roots are matted right on top of this mass of compacted soil. There's a few roots that are growing along this surface, but I can assure you that if you broke this apart, you would not find very many roots penetrating. Now here's an aggregate in the lower right hand part, and you can see that divergent shape that I described to you earlier. Unpredictable, sharp edge, but there you see no roots, no pores, no sign of life in this. So not a very good indicator of soil health or root health or plant health. This, however, looks pretty good to me. I see lots of surfaces where water and air can move. I see lots of places that roots can grow. And if I look at these aggregates, I can also see pores and openings inside the aggregates. So that means roots can explore into the middle of the aggregates as well. So this would be a better sign of soil health. All right, well, this is the end of our talk, and I'd like to encourage you to send any questions that you have to me. Here are my contact information. I also have a Twitter account, a Facebook page, and then the Cooperative Extension web page is up now. And so you should be able to go to this link and then find the under Natural Resources, find the Soil Information page, and you should be able to get to the webinars that have preceded this one, and this one will be posted as well. Well, thank you everybody, and I hope you have a great day.